Good morning, everybody. Praise be to the Lord.
Now and forever.
Now and forever.
So we're going to continue to talk about Sir Isaac Newton, right? And we're going to see to synthesize more about the laws of Isaac Newton. Sorry. So we're going to continue to see another PowerPoint presentation that I already prepared for you, right? About the Newton's laws. It's only a review, actually. Newton's laws of motion. That is the title of this PowerPoint presentation for you, right? It's going to be really helpful for you. Let's see a background, okay? Sir Isaac Newton, born or who lived between the years of 1643 to 1727, was an English scientist and mathematician famous for his discovery of the law of gravity. Also discovered the three laws of motion. He published them in his book Philosophiae Naturalis Principia Mathematica, or Mathematic Principle of Natural Philosophy, in 1687. Today, these laws are known as Newton's laws of motion, and describes the motion of all objects of the scale we experience in our everyday lives. This is a picture of him. If I ever made any valuable discoveries, it has been owing more than patient attention than to any other talent. That said, Sir Isaac Newton. So let's talk about the Newton's laws of motion. An object in motion tends to stay in motion, actually, and an object at rest tends to stay at rest unless acted upon by an unbalanced force. The number two is force equal mass times acceleration. There is the formula in there. For every action, there is an equal and opposite reaction. These one are the three laws of motion of Newton. But let's see the Newton's first law. An object at rest tends to stay and an object in motion tends to stay in motion unless acted upon by an unbalanced force. That is the first law. What does it mean, do you think? Basically, an object will keep doing what it was doing unless acted on by an unbalanced force. If the object was sitting still, it will remain stationary. If it was moving at a constant velocity, it will keep moving. It takes force to change the motion of an object. And what is meant by unbalanced force? For example, if the forces of an object are equal and opposite, they are said to be balanced, and the object experiences no change in motion. If they are not equal and opposite, then the forces are unbalanced, and the notion of the object change. For example, in this case, we can see the graph. The force of the book are balanced, actually. The table pushes upward on the book. Gravity pulls down on the book, actually, right? It's something easy to understand. It's something easy to understand. It's when you put something on the table and you know in that table it's empty place, only the 4 steps, right? If you put something, for example, if I have here in my hand and there is nothing in here, if I put something in, up in on my hand, if I don't have my hand, right, this happened, right? That gravity works, right? But if I put something between the way the object fell down, this is what is the unbalanced force. Something stop, something stop the force of the gravity. That I can put another thing in here and the gravity still works, right? The gravity still works. But if I use something to stop the force of the gravity, that is the meaning of the unbalanced force, okay? Some examples from real life. These are some examples of real life. A soccer ball is sitting at rest. It takes an unbalanced force of a kick to change its motion, right? When you kick it, la tira para otro lado que no sea la meta. Porque ya las dije. Se las tiran de Rubilio, perdón, de Messi, de Ronaldinho y ni a Rubilio Castillo llega. Lo que le gusta jugar fútbol. Another. 2 teams are playing tug of war. They are both exerting equal force on the rope in opposite directions. This balanced force results in no change of motion. Of course, in many ways we play this game, one team will win because are getting more force, right? Newton's first law, it's also called the law of inertia. The inertia, the tendency or inertia is the tendency of an object to resist changes in its state of motion. The first law states that all objects have inertia. The more mass an object has, the more inertia it has, and the harder it is to change its motion, right? For example, or examples in the real life, a powerful locomotive begins with to pull a long line of boxcars that were sitting at the rest. Since the boxcars are so massive, they have a great deal of inertia and it takes a large force to change their motion. Once they are moving, it takes a large force to stop them. For example, if you travel in a train and there is a lot of cars or a lot of wagons, when there is a lot of people, right? There is a lot of wagons in that train. The locomotor, okay, this part of the train need enough force to move all of them. Even need more force to stop all of them because they start to get inertia. They start to get a velocity. All those wagons start to get one same velocity, right? Also, on your way to school, a bug flies into your windshield. Since the bug is small, it has very little inertia and exerts a very small force on your car. So small that you don't even feel it. The thing is, when you travel in the bus of the school or in the car of your parents, and there is a fly on the window, or is a fly flying inside the car, you will see, okay, the car is moving, and if I have something that it's like if I do something like I threw something through the air, but the thing is still moving, right? But if you see the bug in this glider, in this way, the fly is still moving with the car, even if the fly is flying, right? O sea, si usted ve la mosca que está volando, la mosca se debería de detener, ¿correcto? Y pegar con el vidrio de atrás del carro, ¿cierto? Pero la mosca sigue moviéndose de la misma velocidad como se está moviendo el carro. ¿Se han fijado en eso? ¿Por qué? Por el mismo sentido de la inercia. Todo el objeto se mueve a la misma velocidad que se mueven los objetos pequeños. Usted dice, voy en mi carro, yo estoy lanzando una pelota aquí, y la lógica común es que si yo me sigo moviendo, la pelota me viene a pegar acá, al pecho, ¿cierto? No, usted está aquí y la pelota se sigue moviendo a la misma velocidad que el objeto más grande, ¿cierto? Es lo mismo. Yo me sigo moviendo, el objeto que estoy lanzando se sigue moviendo y el objeto más grande se sigue moviendo por la misma inercia. Solo que el objeto más pequeño tiene una inercia más pequeña. A eso me refiero. ¿Sí? La misma velocidad, solo que con inercia menor. Obviamente, entre más grande el objeto, más grande es la inercia. Entre más pequeño el objeto, menor es la inercia. A eso me refiero por si no me entendía. If objects in motion tends to stay in motion, why do moving objects keep moving forever? For example, things don't keep moving forever because there is almost always an unbalanced force acting upon it. Is that thing that I already explained for you, right? For example, a book sliding across a table slows down and stops because of the force of friction. If you throw a ball upward, it will eventually slow down and fall because of the force of gravity. Even in outer space, away from gravity and any source of friction, a rocket, a rocket ship launched with a certain speed and direction will keep going in that same direction and at the same speed forever. Let's talk about the second law, the Newton's second law. Force equal mass time acceleration. There is the formula. F it's equal m times a, right? And the acceleration is a measurement of how quickly an object is changing speed. What does F is equal to ma mean? Or what is the force is equal to mass times acceleration? Force is directly proportional to the mass and acceleration. Imagine a ball of a certain mass moving at a certain acceleration. This ball has a certain force. Now imagine we make the ball twice, a big double the mass, but keep the acceleration constant. F or force is equal to the mass times acceleration says that this new ball has twice the force of that old ball. It's the same. If you have, for example, if you have, I will do this. If you have a marker, right? If you have a marker, this marker, you throw it, has his own acceleration. But if I have a marker with a double of the mass, right? And even with a double of the size, right? With a double of the size, it will get more acceleration, more force. Now imagine the original ball moving at twice the original acceleration. The force is equal to mass times acceleration says that the ball will again have twice the forces of the ball of the original acceleration. Let's see more about this. If you double the mass, you double the force. That is really clear. If you double the acceleration, you double the force. That is also clear too. What if you double the mass and the acceleration? Okay, we have the example in here. You double the mass, you double the acceleration, you have the force in quadruples. So we have in here doubling the mass and the acceleration, quadruples the force. So what if you decrease the mass by a half? How much force would the object have now? Force equal to mass times acceleration basically means that the force of an object comes from its mass and its acceleration. Something very massive, high mass, thus changing speed very slowly, low acceleration, like a glacier, can still have great force. Something very small or low mass, thus changing speed very quickly, high acceleration, like a bullet, can still have a great force. Something very small changing speed very slowly will have a very weak force. Let's talk about the third law of Newton. For every action, there is an equal and opposite reaction. What does this mean? For every force acting on an object, there is an equal force acting in the opposite direction. Right now, gravity is pulling you down in your seat, but Newton's third law says your seat is pushing up against you with equal force. This is why you are not moving. There is a balanced force acting on you. Gravity pulling down, your seat pushing up. Weird. Strange. A beautiful picture of a chair. Wow. Think about it. What happens if you are standing on a skateboard or slippery floor and push against a wall? What happened?
It will take motion. It will take acceleration.
Yes, you slide in the opposite direction, right? It's the same thing that I told you. You kick a ball to a wall, that wall will reflect the force of that ball and send it to another place, right? That is what I'm talking about. You slide in the opposite direction, away from the wall, because you push on the wall by the wall push back on you with equal and opposite force. It's like you, for example, this is the wall and you are here sitting and you only do this, right? You push against the wall. Usted se empuja. Entonces usted se va a mover, ¿correcto? Con la misma fuerza con la que se empujó, ¿cierto? It's the same principle, the same principle. Why does it hurt you so much when you stub your toe? When your toe exerts a force on a rock, that rock exerts an equal force back on your toe. The harder you hit your toe against, it's the more force the rod exerts back on your toe. And the more your toe hurts. O sea que cuando usted patea una piedra, lo que le va a doler es el dedo, no es la piedra en sí. Y mi pregunta es, ¿para qué patea una piedra? Va. Y los que mire que se ríen es porque han pateado piedras. ¡Qué bárbaro! ¿Verdad, Fátima? Pregunto yo, ¿para qué patea piedras, hombre?
Mr. Something different happened to me.
Se le va a paniquear el dedo chiquito por el otro lado.
Mr. Something different happened to me.
¿Mm?
Algo diferente me pasó a mí.
Okay, I imagine what is the something different. What happened to you? You kicked the ball and you fell down.
No.
What happened?
Quería patear una chapita de... Terminé pegándole la patada en la acera.
Ay, muchacho. Ay, sí. Okay, a review. Newton's first law. Objects in motion tend to stay in motion, and objects at rest tend to stay at rest unless acted upon by a balanced force. Newton's second law. Force equals mass times acceleration. Newton's third law. For every action, there is an equal and opposite reaction. And we have our vocabulary for this. Inertia. Inertia is the tendency of an object to resist changes in its state of motion. Acceleration, we have a change in velocity, a measurement of how quickly an object is changing speed, direction, or both. And we have velocity, the rate of change of a position along a straight line with respect to time. We have force, strength, or energy. So, people, this is all about Sir Isaac Newton, her studies and his studies and his discoveries. So let's watch two videos. We're going to watch two videos about Newton, right? About Newton's first law that is really helpful for you.
Imagine you're sitting on a recliner chair watching your favorite movie on a lazy Sunday. And your mom calls out your name and asks you to run some errands. You can imagine how difficult it would be for you to get up and do the work. Imagine you're practicing for your 100 meters race on this track, and somebody asks you to stop immediately within a second. Will you be able to do it? What if you're suddenly asked to turn towards the right? Will you be able to turn immediately? The answer to both the questions would be a no. You can stop, yes, but gradually. You can also turn, but not sharply. And guess what? It's the same story with every object. Every object will continue to do what it's doing. If it's at rest, it will remain at rest. And if it's in motion, it will stay in motion. But what can change this? Yes, only an unbalanced force can change this. If it's at rest and an unbalanced force acts on it, it will move. If it's in constant motion, and an unbalanced force acts on it, it may accelerate or change direction. And this is nothing but the Newton's first law of motion. Here's the correct definition. An object at rest stays at rest, and an object in motion stays in motion with the same speed and the same direction, unless acted upon by an unbalanced force. In simple words, it means that the objects continue to do what they're doing unless some external unbalanced force acts on them. We can also understand this using a simple diagram. If the forces are balanced, there can be two cases. An object may be at rest, or an object will be in motion at a non-zero constant velocity in a particular direction. These can be the only two cases when the forces are balanced. In the first case, the object will continue to remain at rest, and in the second, the object will continue to stay in motion at the same velocity and in the same direction. Don't forget, these two cases will remain true only if the forces are balanced. In the next video, we will look at a few applications of the first law of motion. EVE Online is a vast... Do you remember the Newton's first law of motion? It says that an object will continue to do what it's doing unless acted upon by an unbalanced force or some net force. Now the important question is, what happens when there is net force acting on an object? That's precisely what the second law of motion will discuss. Do you remember understanding the first law of motion with a simple diagram? If the forces are balanced, the acceleration will be zero. In the first case, the object will continue to remain at rest, and in the second, the object will continue to stay in motion at the same velocity and in the same direction. Don't forget, these two cases will remain true only if the forces are balanced, only if the net force is zero. Now let's try to create a similar diagram for the second case. If the forces are unbalanced, then there will be acceleration. We saw that in the previous video. And now we come to the interesting part. Let me ask you a question, and I'm sure you can answer it. On which two factors do you think the acceleration will depend on? I want you to tax your brain a bit. Let me repeat my question. On which two factors do you think will the acceleration depend on? Okay, let's say there's an object on a table. You apply a net force of 10 units on it. And then you apply a net force of 20 units on it. In which case do you think the acceleration will be more? Of course, the one in which the force was more. So we can say that one of the things the acceleration depends on is net force. If it's more, then more will be the acceleration. If it's less, then lesser will be the acceleration. Acceleration depends directly on the net force. Come on, now I want you to think about the second quantity the acceleration will depend on. Let's say there are two objects on the table. One has a mass of 3 kilograms and the other has a mass of 5 kilograms. Now, if you apply net force of 10 units to each of them, which one do you think will accelerate more? Surely it's the 3 kg one because it has lesser mass. Lesser the mass, more the acceleration. And more the mass, lesser the acceleration. Hence, we can say that acceleration depends inversely on the object's mass. If you understand this concept well, then understanding the second law of motion will be very easy. Mathematically, it can be written like this. In simple terms, the acceleration is directly proportional to the net force applied and inversely proportional to the mass of the object. That's the second law. Or as more people understand it, like this. The net force is the product of mass and acceleration. With this, can you tell me the units of force? That should be easy. The standard unit of mass is kilograms, and that of acceleration is meters per second squared. So the unit of force is kilograms times meters per second squared. And this is what we call as Newton. 1 Newton is 1 kilogram times meters per second squared. So if the mass of the object is 10 kilograms and the acceleration is 10 meters per second squared, then the force will equal 100 newtons. We can say that 1 Newton is defined as the amount of force required to give a 1 kilogram mass and acceleration of 1 meter per second squared.
Mister, sorry about my internet connection.
The only question you need to ask yourself while studying the third law is, what happens when two objects interact with each other? What happens when you place an object on the table? The object exerts a force on the table and the subject exerts an upward force on the object. There are two forces that result from this interaction: a force on the table and a force on the object. The magnitudes of the two forces are the same, but the directions are opposite. These forces are called as action and reaction forces. The force exerted by the object on the table was an action force, and the force exerted by the table on the object is the reaction force. What we saw here is nothing but a display of the Newton's third law of motion. Every action has an equal and opposite reaction. That's how simple the third law is. Every action has an equal and opposite reaction. It means that when two objects interact, there is a force on each object. The magnitude of force on the first object equals the magnitude of force on the second one. And what about the direction? The direction of force on the first object is opposite to the direction of force on the second one. Let's talk about more examples. While a frog is swimming, it pushes the water back and the water pushes its body forward. Now let me ask you a question. Say a bird is flying upwards. Will the Newton's third law apply here? Sometimes the third law is not so obvious. You'd probably say that the bird is the only object here and there's no second object. But that's not correct. The wings of the bird push the air downwards and the air pushes the bird upwards. Action and reaction forces make it possible for birds to fly. We take one last example to understand something very interesting about the third law. What happens when a gun is fired? You're right, it exerts a forward force on the bullet. And the bullet exerts an equal and opposite reaction force on the gun. And this exists in recoil of the gun. A perfect example of Newton's third law. But hold on. If the force exerted by the gun on the bullet is the same as the force exerted by the bullet on the gun, then why doesn't the gun recoil with the same acceleration as the bullet? The gun recoils, yes, but it doesn't recoil at the same acceleration as the bullet, right? Same magnitude of forces, but different accelerations. Why do you think this happens? Okay, so if your concept of the second law of motion was clear, you wouldn't really be surprised with this. The second law of motion says that the force is the product of the object's mass and acceleration. Or the acceleration of the object is equal to the force over its mass. What does this tell us? Yes, if the mass is more, then the acceleration will be less. In this example, the mass of the gun is much more than that of the bullet. Hence, the acceleration of the rifle is lesser than that of the bullet. If you're in a boat and step out of it onto the land, there are two forces involved. You pushing the boat behind and the boat pushing you forward. And that's why you see the boat go behind when you go forward. Now let's say a sailor jumps off a huge ship. The sailor does apply a force on the ship, and the ship also applies a force on the sailor. But do you think the ship will accelerate as much as the sailor? Not really. And I think you know why.
Hi, I'm Brad Callen, and in this video,
Okay, I see you at 10:50 for the class of spelling. Bye-bye. Take care.
Bye.
Bye, Mr.
Bye, mister.